Toshiba Device and Storage Corporation. E-learning. Basics of op-amps. This course is intended for beginners and explains the characteristics, basic operation, internal operation, and negative feedback of op-amps as well as the electrical characteristics specific to them. Chapter 2. Using an op-amp. Using an op-amp. An op-amp has a high gain as shown in figure. The gain is dependent on frequency. The gain also varies from device to device and is affected by temperature and other environmental conditions. Therefore, op-amps are generally used with negative feedback. Depending on conditions, negative feedback turns into positive feedback, causing the feedback loop to oscillate abnormally. Section 2 describes feedback oscillation, basic amplifier circuits using an op-amp. A virtual short circuit required when considering an amplifier circuit. 1. Feedback, positive and negative feedback. Op-amps are generally used with negative feedback. This section briefly describes negative feedback. There are two types of feedback loops, positive and negative. For example, positive feedback can be compared to the following cycle. 1. You study hard, and your grades improve. 2. As your grades improve, studying becomes more enjoyable, and you study more. 3. Your grades improve further. In other words, positive feedback is a process that further increases the effects of a small change in output. In contrast, negative feedback can be compared to the following cycle. 1. You study hard, and your grades improve. 2. You spend less time studying and more time relaxing. 3. Your grades drop. 4. You spend less time relaxing and more time studying. 5. Your grades get back to the previous level. It is a process of trying to keep the results, i.e., your grades in this example, constant. This process is called negative feedback. Figure shows an amplifier circuit with feedback. It consists of an amplifier, a feedback circuit, and an adder, or a subtractor. AV is the open loop gain of the amplifier, and B is the feedback factor. The amplifier amplifies the input signal and outputs an amplified signal. Part of the output is returned to the input of the amplifier via the feedback circuit and the adder. When Vin changes, negative feedback changes the input to the amplifier in order to counteract the effect of the change in Vin. Conversely, positive feedback increases the effects of the change in Vin. The output, Vout, is equal to the sum of the Vin and feedback signals multiplied by the open loop gain of the amplifier. This can be rewritten as follows. If the feedback signal, AV times B times Vout, has the same phase as the Vin signal, the amplifier circuit has positive feedback. If the feedback signal has the opposite phase to the Vin signal, the amplifier circuit has negative feedback. Although an op-amp has a very high open loop gain, it is difficult to use because of its frequency dependence, see next section. Therefore, an op-amp is generally used with negative feedback. Negative feedback causes its gain to decrease substantially. On the other hand, negative feedback increases the frequency bandwidth in which the gain curve remains flat and decreases the output impedance. In addition, negative feedback makes it possible to create an easy-to-handle amplifier because it compensates for variations in gain. Normally, positive feedback is not used for amplifiers. For example, positive feedback is used to provide hysteresis for oscillators and comparators. If you are interested in this, see the FAQ entry, How can I provide hysteresis, Schmidt trigger, for a comparator? 2. Open loop and closed loop gains, increasing the bandwidth of an amplifier. The open loop gain, GV, of an op-amp has the same frequency characteristics as a first-order RC low-pass filter as shown in figure. At frequencies higher than the corner frequency, FC, at which the open loop gain is 3 dB lower than the DC gain, the open loop gain decreases at a rate of 6 dB per octave, 20 dB per decade. In this frequency range, the decibel open loop gain of the op-amp, GV, decreases by 6 dB, i.e., the linear open loop gain, AV, halves, when the frequency doubles. Hence, the frequency at which the gain is equal to 1, 0 dB is called the unity gain cross frequency, FT. Therefore, the above equation can be restated as follows. This is called the gain bandwidth product, designated as GBWP, GBW, GBP, or GB. Note that this equation is true in the frequency range in which the open loop gain decreases at a rate of 6 dB per octave. Now, let's consider what occurs when an input signal with a frequency of 2 ± 1 kHz is applied to an op-amp that has frequency characteristics as shown in figure. In the case of an op-amp under this condition, the gain at 3 kHz is roughly 10 dB lower than the gain at 1 kHz. Normally, the op-amp cannot be used under this condition. Negative feedback solves this issue. As mentioned in the previous section, when an op-amp is used as an amplifier, it is usually used with negative feedback. The figure shows an amplifier circuit with feedback. The input, Vin, and the output, Vout, have the following relationship. This relationship is called the closed-loop gain, represented as GCL in decibel scale and ACL in linear scale. The 20 log rule is used to convert a linear voltage gain into a decibel voltage gain, G equals 20 times log A. Where AV is the open-loop gain of an amplifier and B is the feedback factor. AV times B is called the loop gain. The denominator, 1 plus AV times B, is called the amount of feedback. In the case of negative feedback, the loop gain is less than 0. An op-amp has a very high AV, hence, the loop gain is greater than 1. Therefore, the amount of feedback is calculated as follows. Hence, the above equation can be simplified as follows. Figure shows this relationship. The op-amp has a bandwidth of Fc. With negative feedback, its closed-loop bandwidth expands to FCL. FCL is calculated as follows from the gain bandwidth product equation. When the closed-loop gain, GCL, or the bandwidth, FCL, is insufficient, it is necessary to select an op-amp with high FT. 3. Oscillation. An op-amp is normally used with the feedback circuit as shown in figure. There are two types of feedback, positive and negative, as described in section 1. When an op-amp is used as an amplifier, it is configured for negative feedback. Care is required as to the oscillation of a feedback circuit. A signal or noise that acts as a source of oscillation can develop into oscillation under certain conditions. Here is a brief explanation about oscillation. A source of oscillation applied to the input passes through the amplifier in the feedback circuit. Then, the adder adds it to the Vin input. Therefore, the output of the adder becomes larger than the initial state. As this process is repeated, the source of oscillation grows, causing oscillation. This is the characteristic of positive feedback. You might think that oscillation is irrelevant as you use negative feedback. Even if it is negative feedback for the signal to be amplified, it might turn into positive feedback in the higher frequency band. Let the open loop gain of the op-amp be AV and the feedback factor be B. Then, the transfer function of a feedback circuit is expressed as follows. Both AV and B are complex numbers. In the case of a negative feedback circuit, the following relation holds. Therefore, Vout provides a stable output as described in section 1. However, the phase of the output lags that of the input at high frequency since all circuits have a delay. The feedback circuit turns into a positive feedback loop when this phase lag reaches 180 degrees. The waveform of the output, Vout, differs as shown below, depending on the magnitude of the loop gain of positive feedback, i.e., when the signal from the feedback circuit has the same phase as the input signal. When a source of oscillation is applied to the input, a damped, sustained, or explosive oscillation occurs, depending on the magnitude of the loop gain at the frequency of the oscillation source. Generally, a sustained oscillation is called an oscillation. An explosive oscillation eventually subsides to a sustained oscillation since the open loop gain, AV, is restricted by the dynamic range of the amplifier. A sustained oscillation occurs when the loop gain satisfies the following condition, i.e., the denominator of the transfer function becomes 0. This condition is called the Barkhausen condition for oscillation, or simply oscillation condition. Note that an explosive oscillation eventually subsides to a sustained oscillation as described above. Therefore, the amplitude condition that causes abnormal oscillation is as follows. Because of an internal parasitic capacitance, an op-amp has a first-order delay element, as is the case with the first-order low-pass filter, as shown in figure. In the case of typical op-amps, the cutoff frequency of open-loop gain response is between 10 Hz and 100 Hz. The phase of the output lags 45 degrees behind in this frequency range. The phase lag is 90 degrees in the frequency range in which the open-loop gain decreases at a rate of 6 dB per octave. If the gain vs frequency curve has such characteristics with only a main pole, a margin of 90 degrees remains until oscillation occurs. Therefore, oscillation is unlikely to occur. In reality, an op-amp has multiple poles. The cutoff frequency, Fc, shown in figure is called the main pole. The frequency pole at Fc2 close to the unity gain cross frequency, Ft, is called a second pole. Although there are more poles at higher frequencies, they do not cause any practical problem. As shown in figure, the slope of the open loop gain curve changes from 6 dB per octave to 12 dB per octave at Fc2. The phase lag also increases further by another 45 degrees. This phase lag does not cause any problem when Fc2 is higher than the unity gain cross frequency, Ft. However, even when FC2 is lower than FT, care should be taken when using op-amps as unity gain amplifiers such as voltage followers. If the datasheet for an op-amp states that it can be used with unity gain, it has a second pole at a frequency higher than FT. In order to avoid abnormal oscillation, an op-amp should be used in the frequency range, FC to FC2, in which the open loop gain decreases at a rate of 6 dB per octave. Note, however, that, at a frequency close to FC2, an op-amp is affected by a second pole, causing a power loss and a phase delay. To avoid its effects completely, the closed-loop bandwidth, FCL, should be less than 1/5 of FC2. Noise gain and loop gain are also related to oscillation. For details, please refer to our application note Basics of Operational Amplifiers and Comparators. The above is a discussion on the oscillation of an op-amp itself. It is also necessary to ensure that external circuitry is also free from oscillation, e.g., phase delay. For example, this consideration applies to an application in which a capacitive load is driven by an op-amp. Oscillation occurs if the cutoff frequency due to the capacitive load is within the range in which the loop gain is greater than 1. In order to prevent oscillation, it is necessary, for example, to add a resistor in series with the capacitor. Even when an op-amp is not connected with the load, care should be taken as to wire or other capacitance. Minimize the length of the wire from the op-amp output to the subsequent device and that of the feedback loop. 4. Basic op-amp applications. In the most basic form, op-amps are used as non-inverting amplifiers and inverting amplifiers. Both non-inverting and inverting amplifiers have negative feedback, with the output connected to Vin minus, as described in the previous section. The closed-loop gain, ACL, is shown in the following figures. The gain can be calculated easily by using the concept of a virtual short circuit, also known as a virtual short, virtual ground or imaginary short, described in the next section. The non-inverting amplifiers have a very high input impedance since their input is directly connected to an op-amp. In contrast, the input impedance of the inverting amplifier is lower than that of the non-inverting amplifier because Vin minus and Vin plus have the same potential as they are virtually short-circuited and because R1 acts as input impedance. Figure shows a voltage follower. The voltage follower can be regarded as a non-inverting amplifier with an R1 of infinite resistance and an R2 of 0. Since the voltage follower has a low gain, unity gain, AV equals 1, it has a wide bandwidth. Therefore, care should be taken since it is susceptible to the effect of a second pole as discussed in section 3, oscillation. Most op-amps can be used as unity gain amplifiers since they have a second pole at a frequency sufficiently higher than the unity gain cross frequency, FT. However, they might go into oscillation because of wire or load capacitance. If the datasheet for a given op-amp states that it can be used at a unity gain, it can be used as a voltage follower. Contact Toshiba's sales representative if you want to use any other op-amp as a voltage follower. In addition, op-amps have various applications, including a differential amplifier, subtraction circuit, as well as an adder and integrator circuits. 5. Virtual short, virtual ground. The closed-loop gain of an op-amp with negative feedback can be calculated easily using the concept of a virtual short circuit, also known as a virtual short or virtual ground. The concept of a virtual short is that the Vin plus and Vin minus terminals of an op-amp with negative feedback have almost the same potential regardless of the input signal when it has a large open-loop gain. Consider as follows to intuitively understand a virtual short. An op-amp amplifies a difference in voltage between Vin plus and Vin minus by a factor of 100,000 or more, called the open-loop gain. However, a real op-amp has a finite output. Therefore, in a circuit without negative feedback, if the differential voltage is a sine wave of 1 VPP, the output should be 100,000 VPP, but generally the output is limited by the power supply voltage and ground. As a result, it becomes a saturated square wave at the voltage between the supply voltage and ground. Therefore, when a distortion-free output is obtained with an amplifier using an op-amp, the difference in voltage between the Vin plus and Vin minus inputs should be negligible. In the case of the negative feedback amplifier, inverting amplifier, shown in figure, the output is connected to the input in such a manner that an increase in output causes a decrease in input. As a result, the output signal fits between the power supply and ground. Suppose, for example, that an inverting amplifier has an input voltage of 1 VPP and a gain of 3, R2 equals 3 times R1. Then, the output voltage becomes 3 VPP. At this time, the op-amp is operating with an open-loop gain of 100,000. Since the output voltage is 3 VPP, the input voltage is 3 VPP divided by 100,000 equals 30 micro VPP. Hence, Vin minus is approximately equal to Vin plus. Next, let's use simple calculations to understand this. Figure shows a negative feedback amplifier, inverting amplifier, using an op-amp. Suppose that the op-amp is the ideal one. Then, the following are true. 1. Infinite open loop gain, AV. 2. Infinite input impedance. 3. Zero output impedance. Since the input impedance is infinite, all of the current flowing through R1, I1, flows through R2. The output voltage of the op-amp is given by the equation. From equations 1 and 2, Vn plus is calculated as follows. Because the output impedance is 0, we obtain Vn plus equals Vn minus from equation 3. Hence, the voltage at the Vn minus input is equal to that of the Vn plus input connected to ground. In this case, the condition of the Vn minus input is called the virtual short. Next, let's calculate the closed loop gain, AV, of the non-inverting amplifier shown in figure using a virtual short and the ideal op-amp. Let's express the output voltage, VO, as a function of Vi. From the concept of a virtual short, Vn minus equals Vn plus equals Vi. Therefore, the current flowing through R1, I1, is calculated as follows. No current flows to the op-amp input since it has infinite impedance. Letting the current flowing through R2 be I2, I1 equals I2. Hence, the voltage across R2, VR2, is as follows. Hence, VO is calculated as follows. You can easily find the closed loop gain equation. The closed loop gain, AV, of the inverting amplifier shown in figure can also be calculated in the same manner. Hence, the closed loop gain is as follows. As described above, the closed loop gain can be calculated easily using the concepts of a virtual short and the ideal op-amp.